Hi, so good morning. I'm very happy to give these lectures on multi-messenger astronomy. Just by way of introduction, my name is Zoltan. I was until recently for a very long time at Columbia University in New York. I moved last week, starting a new position at this institute called ISTA. I work on many things in astronomy and astrophysics and cosmology, including mergers of black holes when they're not in vacuum, but surrounded in astrophysical context, surrounded by, I'm mostly interested in surrounded by gas. So you'll hear a lot about that. I would say everything has been great. I really love Vienna so far. I love the institute. I did have a bike crash, which resulted in this surgery, so I have only one fully functional hand for now. This is the institute, just so you know, and it's located outside Vienna. We are here, and this institute is about 45 minutes by public transport from here. I think I will skip a more detailed description, but it's an exciting new institute. So the idea, the overall idea of these two lectures is to dwell on this idea that there are many ways to observe the universe and make inferences about what's going on, and different types of observations. And I listed here the four main categories. You can debate these, but the traditional way is to look at photons, electromagnetic radiation. There's also particles, high-energy particles coming from distant extragalactic sources. By the way, I'm mostly interested in extragalactic sources, but maybe I'll comment a bit on our Milky Way. Then there's also neutrinos, which we use to observe phenomena. And then most recently, topic of the school is gravitational waves. A key point is that these types of observations are often sensitive to different aspects of a physical system. So the system of most interest to us is, for example, in the galactic nucleus, there's a black hole. If there's two black holes, there will be gravitational waves coming from the very bottom here. There might be an accretion disk fueling them, and that causes dissipation and electromagnetic emission. And then in the jets that come out, there are cosmic rays generated, and high-energy particles accelerated, and neutrinos are produced, and we can observe all four of these. Now, what makes most sense to focus on, there are certain combinations which allow you to do new science. So, since this school is about gravitational waves, I think I would say the most interesting things we can do is when there's some scientific question you can answer or study only when you have combination of gravitational waves, or let's say photons, or gravitational waves plus high-energy particles, or gravitational waves in multiple frequencies. And otherwise, you cannot do it with just gravitational waves or with just photons. So this is what I would call multi-messenger astronomy. One slide on the history, just to also imprint on your idea that some of this is very old, some of this is very new. Obviously, we've seen photons forever, ever since we looked up on the sky. Maybe you can start observing photons from 1608, when the first telescope was pointed on the sky. Now, cosmic rays were also detected, I would call them old, over 100 years ago. And actually, just to make a point, that the cosmic rays were detected in 1912 in this balloon experiment. This guy over here is Victor Hess. He was Austrian. He was here at the University of Vienna. And he got the Nobel Prize in 1936 for discovering cosmic rays. Neutrinos have also been detected for a while, but the interesting ones for us are extragalactic neutrinos, which were first detected a little over 10 years ago by this experiment called IceCube on the South Pole. Before then, we had neutrinos from the sun and from nuclear reactors that produce neutrinos. And then, of course, gravitational waves, I don't have to tell you, is discovered 10 years ago, 11 years ago by the LIGO experiment, and Virgo and Kager. Okay. Now, I assume that you're at this school, so you all know that there are different kinds of gravitational waves and different kinds of instruments to detect them. This is just the collage showing frequency here, characteristic strain, and this is just the cartoon, but this is the ground-based experiments LIGO. These are, and you know, they're based on laser interferometry. Then this is the space version, LISA, which will be launched in 10 years or so. And then pulsar timing experiments will probe even more massive black holes. I'm sure you've heard this already, but you basically divide the orbital time at the Schwarzschild radius that gives you the frequency. And for big black holes, that's longer. The perimeter of the black hole is much longer. And so the frequencies are much lower. Do I have to tell you about pulsar timing arrays? I assume somebody else will talk about this. Actually, pause. Can you raise your hand if you're a postdoc? Can you raise your hand if you're, by your own judgment, on the second half of your PhD? And by your own judgment, the first half of your PhD? Good. It's just useful for me to know how fast to go. So I'm not going to describe this, but I should also say, feel free to interrupt. We have 80 minutes today, 80 minutes tomorrow. I'm more interested in making sure everybody understands things than jogging through all my slides, which are anyway too many of them. Okay, so the reason I show this, which you've probably seen before, is to explain why I made a decision 15 years ago to spend my time mostly researching massive black holes and not stellar mass black holes. And that was because the conventional wisdom is that these big black holes, they reside in the nuclei of galaxies. And since we are interested in the merger, that merger is of the black holes. That pair of black holes is conventional wisdom produced in the mergers of galaxies. And I'll describe to you in some more detail. Mergers of galaxies bring in gas. So this merger, if you have to make a naive guess, is happening in the binary being embedded in a dense gas cloud. I thought that was much more interesting for astrophysicists to think about. The leading candidates for how to produce stellar mass black hole mergers, again, I'm not sure here how many you have heard a detailed analysis of how LIGO mergers are created, but in the two main channels of producing those LIGO mergers, it happens in vacuum. Either due to n-body processes in dense stellar clusters or galactic nuclei, or in a binary stellar evolution, which ejects the gas before the merger takes place. So the conventional wisdom is that this is in vacuum. So if you want to combine gravitational waves with something else, maybe this is more appealing. I, of course, put question marks here because this could easily be reversed in principle. Okay. So, I should say that mass, in terms of just gravitational waves themselves, doesn't really matter. I'm sure you heard by now, Cliff will give a talk yesterday and will give a talk today. The waveform produced by a binary coalescence is independent of mass. If there was nothing else, so this shows actually, this is from the paper from LIGO, the first discovery of the first coalescence. This is the in-spiral and merger extracted from the data. But this would look exactly the same for massive black holes if it was in vacuum. If it's not in vacuum, then this can be distorted, and I'll get to that as a part of multi-messenger astrophysics. Okay, so now I'm going to have this slide, which I have to tell you upfront. What are interesting science questions? And there's quite a lot here, but I'm going to go through these points so that if anything you go out, you know that these are exciting new science things you can do with multi-messenger astronomy. And so I divided these into three categories. One is if you're more into astronomy and astrophysics, what can gravitational wave plus photons or something else do for you. If you're more into fundamental physics or cosmology, and then if you're working on the instrument or detections, just practical issues can also be important. So let me go through these. So if you're interested in astronomy and astrophysics, there's here accretion physics, electromagnetic emission with known black hole parameters. So here the novelty is you detect a gravitational wave source, which if you want to concretely have in mind the massive black hole merger by LISA or that's surrounded by some gas. So then the gravitational wave observations fix the mass. LISA will have high signal to noise measurements, will fix the spins and the orbital parameters. And now if you detect, if you can associate this object on the sky with the actual electromagnetic source, then you can study the light curve of this source over time, the spectrum of this source with known black hole parameters. So that will be completely novel way to do accretion physics. How does a known black hole with known spin accrete and shine? I wrote here distorted gravitational waves. Oh, by the way, so I marked in blue things which really require you to have the same source detected in gravitational waves and in photons. I also like to broaden this category and just say there are lots of things where you don't actually necessarily have to detect the same source, maybe same population of sources in photons and gravitational waves, or you can do more if you detect the gravitational wave source in photons. For example, here, what I just said before, suppose you detect a gravitational wave source and the waveform doesn't look exactly like in vacuum, it looks a bit different. Then, of course, you can think of systematic errors, etc. But let's say you've taken care of everything and you've convinced yourself there's some distortion of the waveform and you blame it on the environment. If your two black holes sit in an accretion disk, this tells you something about the accretion risk, in particular the mass and the mass and the temperature of the accretion disk, as I'll explain hopefully. Now, this means you know what kind of gas surrounds this black hole binary. If you also detect it in photons, you get to study quasars, and you study the accretion disk of particular quasars. This is particularly important because the gravitational wave distortions will be sensitive to most of the mass. If you have a gas cloud or disk around the binary, these distortions will be produced by where most of the mass is of the gas. We actually don't get to see most of the gas mass in quasars because they're very optically thick. The emission, you see the top layers of a very optically thick gas disk. That's the standard notion. So we don't actually get to see into the disk. That was only one bullet. The other obvious point is, I don't know how many of you do astronomy for PhD, but there's a very, very popular question to study in astronomy, which is that quasars, which are active black holes, seem to leave behind remnants whose mass correlates with the mass of the galaxy. And this led to this notion that galaxies and their central black holes, which are really, really tiny, in principle, they could be completely decoupled from the rest of the galaxy because you're talking about such huge, many, many orders of different scales. Yet they seem to co-evolve. The black hole mass correlates with the mass of the whole galaxy. And this is true over a limited range of redshift. Now, if you detect gravitational sources which are merging, you know the masses of these sources. And now you map out over redshift mergers of black holes of different masses. And then you observe them in photons, you know which galaxies they sit in. So you have direct measurement of the assembly of the galaxies and the black holes over cosmic time. Question? Yeah, feel free to. Yeah. Okay, so that's a very good question. And the answer is that you should be doing that, but we have essentially very limited predictions for these distortions. In my case, I think the most conservative thing to say is gas surrounds the black holes. The gas torques the in-spiraling black hole binary, distorts it. We have a few simulations, and you can't really do analytic calculations for this. I will actually go through that a bit, because they've been proven already by simulations to be not so accurate. We would really need a grid of simulations where you parameterize some model, and then you fit the data with a parametric gas distortion model. And also, if you think there's dark matter around the binaries, which causes the in-spiral to deviate, you should model that, and everything should be together. We're nowhere near doing this. Nobody's doing this. It's for people in the room. You have 5-10 years before Lisa flies. That's a good topic, actually. Very, very at the baby stage. Okay. I think another topic I like, because it's one of my own research subjects, is how do massive black holes come about in the first place? If you pay attention, you know that James Webb Space Telescope have already found very, very high redshift, up to redshift 10, massive black holes powering quasars. And how these first black holes come about, and how did they grow so big so quickly in a few hundred million years of the universe? Well, if we have gravitational wave data, we can probe how they're assembling at very high redshift due to mergers. That's a process by which you can grow black holes. And if you also have electromagnetic observations, then you can study how they grow by accreting. If you combine these two, you kind of have both ways to probe early growth of black holes, which is one of the other very exciting frontiers in astronomy. Okay, here's another question I like. As you know, there are two types of black holes I mentioned already. Stellar mass, we know how they form, roughly. When stars run out of fuel, if they're very massive, they leave stellar mass black hole remnants. We have supermassive black holes. We know when they're in the centers of galaxies, but there's a large gap between, let's say, from 100 solar masses to 10 to the 5 or 6 solar masses, where observationally it's very hard to find intermediate mass black holes, and we don't really know if they exist or not, at least not in large numbers as a population. So again, you can detect these intermediate mass black holes in principle by gravitational wave detectors. LISA will be sensitive to these. In the future, Einstein telescope will be sensitive to these. And if you have also electromagnetic observations, you can figure out which galaxy they form and how often, and you can study formation of these intermediate mass black holes. Now, going down to stellar mass binaries, I hope to get to this topic in some more detail, but I think for me, one of the most, in fact, to confess, the most interesting thing that LIGO has delivered among the many other amazing things is this question of what astrophysical process produced the events that we detect. It's clear that there was some astrophysics involved to make such close pairs of black holes. And if you have gravitational signals, well, we already have 190 events. Soon there will be a few hundred events. We still don't really know. I'm sure you've heard this. We cannot say any particular event or even the population of sources where they came from. If you can combine, if they emit photons, which is less clear, as I said, if these stellar mass binaries somehow emit photons, it will, or cosmic rays, or it will surely help pin down astrophysical way that they arose. Going through 2 more points about stellar mass black hole stellar mass objects. In another source is double white dwarfs. They will be detected at high signal to noise in some cases with the LISA detector. And those white dwarfs are not black holes. They have material. They can interact tidally, deform each other, transfer mass from one white dwarf to another. This is another big topic. And if you see both the radiation and the gravitational waves from these, you can study the physics of mass transfer. And I also just like to include, in principle, gravitational wave population of white dwarfs can trace out the structure of the Milky Way, including the bar and the bulge of the Milky Way. And we can compare that, of course, with electromagnetic observations of the Milky Way. It will be great. I think there's probably a couple others which other people are excited about. Hopefully this convinces you that it's a pretty nice prospect for the future. Any questions? Yeah.
There's many students that
Yes, correct. And I'm up to here. I'm basically up to the last three are stellar mass. The above, I'm thinking of massive black holes, galactic nuclei with gas. I will actually explain that in some great detail in a second. Other questions? Okay, so cosmology in fundamental physics. The one thing I'm sure everybody has heard about is the Hubble diagrams from standard sirens. Actually, can you raise it? This must have come up in the school. Can you raise your hand if you haven't heard of this? So I would say maybe just a few words. As you know, the universe is accelerating its expansion, and this was discovered with supernovae. And the way it was discovered with supernovae is that for a supernova, you take a spectrum, you look at some lines, you know the redshift of the source. And then some clever methods were employed to measure the distance to the supernova. And then you make a plot of distance versus redshift, which depends on your cosmological model. This concept is pretty simple. The amazing or amusing thing is that for a supernova, the distance is very hard to measure. There's an explosion in the sky, it goes bright and then fades, and there's a spectrum, but how do you know how far it was? It could be farther, but intrinsically brighter, or it could be closer to us and intrinsically fainter, and then we don't know the distance. So there was some empirical calibration that had to be used. And it was quite good. They got Nobel Prize for that. Now, a gravitational wave source is the complete opposite of this. Because for a gravitational wave source, if it's in spiraling, you can immediately measure the distance just from the gravitational waves. Did Cliff Will explain this? Does that puzzle people actually?
there will be
yeah.
So I'm sure that.
Okay, I just add my one sentence on this. I think this puzzles people. When you first hear, how do you know it's not further away and a bigger black hole, or closer to you and a smaller black hole merger? And the answer is very simple. Is that degeneracy is broken, because if it's intrinsically bigger black hole, it's inspiraling faster. If you measure the frequency evolution and the frequency and the amplitude, these three can be combined to measure the distance. So that's great, but the problem is that if it's in vacuum, we have no idea of the redshift. If it will be explained, I think, in future lecture, then that you can only measure the so-called redshifted chirp mass, which is the mass times 1 plus the redshift. So we're not able to do this exercise of plotting redshift versus distance. But if you measure the same gravitational wave source in some telescope and measure its spectrum, you can measure the redshift, just like for supernovae. Here the challenge is to identify either the black hole, the accreting black hole binary itself, or its host galaxy to measure a redshift. And then once you do that, you can measure distance redshift relation and do cosmology. But this will be revolutionary because supernovae are limited. We only see them at 2 redshift, maybe 1. LISA will see sources essentially, and the Einstein telescope, eventually to anywhere in the universe. So we can go to very high redshift, and also there's no systematics involved in terms of building this distance ladder, which is eternal consternation for supernova measurements. The distance measurements are empirical and calibrated local Cepheids. So, okay. For me, the most interesting or exciting point is that you could actually combine these two. you could make a this so-called Hubble diagram from standard sirens, so that's the gravitational source, and standard candle, that's the supernovae. You can make a relation, distance versus redshift. If you compare supernovae and gravitational wave sources, in principle, they should agree because gravitons travel at the speed of light, just like photons. And so if gravity was given by general relativity, then these two diagrams should agree. If there's something wrong with gravitational theory on cosmological scales, for example, an example of that would be extra dimensions, for example. That's a topic in particle physics, where gravity gets weaker in certain models at very large distances because the gravitons leave our 3+1 dimensions and go to some other dimension over a characteristic distance scale. So you can have weakened gravity. You can also have gravitons being not massless particles, but massive particles, in which case they travel at speeds which are less than the speed of light. So you can compare these diagrams and study these things, either through the arrival time of photons versus gravitons, or just the difference between the diagrams. So there's limits. So in fact, this experiment, where you look at the delay time between photons and gravitons, it's already been done. And in fact, I should have emphasized more. That's an example of multi-messenger astrophysics already. So in the LIGO experiment, none of the black hole mergers had an electromagnetic counterpart on the sky, but the neutron star merger did. The neutron star merger detected by LIGO was timed. The photons, there was a kilonova explosion, which actually I don't think I'll go to in too much detail, but there's a kilonova. And there were actually also gamma rays coming from this source, gamma ray burst. So the gamma ray burst could be timed with compared with the gravitational waves. And that, what happens is that gives you a limit on the mass of the graviton. So if the gravitons travel at very close to the speed of light, then that's allowed. They cannot be much slower. And that difference is already very small. There's two reasons this will be even more interesting with LISA, for example. One is that in this case, you have to actually model the source. You have to have an astrophysical model for the gamma ray burst. When you smoosh two neutron stars together, it's not obvious when the radiation is produced and when the photons leave the source, right? You want to do experiment where you compare their time of travel and you measure at the end, you have to know the beginning, when they left. So you have to do some modeling, so the results depend on the model. It will be very interesting to repeat this, where you actually see the in spiral, and you see some photon signal, which has the same fluctuating in spiral shape, then there will be no ambiguity in the phasing comparison of the phases. In the future, this can be improved a lot with LISA. Is that okay? Last point on this, if you measure the gravitational wave from the binary, you measure the frequency of the gravitational waves, and you use this equation, the energy, h times the frequency, should be equal to the gamma mc squared if the graviton is massive. So you can actually check this equation. Gamma is the Lorentz factor that depends on the velocity of the gravitational waves. So this equation should be, you can check it. If you measure, so F is from gravitational waves, H is Planck's constant. Gamma is measured by the velocity of the gravitational waves from a time of arrival difference. Is the speed of light, so therefore you measure the mass of the graviton, but you can do this at different frequencies. You can check that this equation holds, you are effectively probing Lorentz invariance this way. Okay, there's three more things, and these are slightly different. So inflation also produces gravitational waves. I didn't include it in my diagram. They're extremely low frequency gravitational waves. and we can measure them. I won't go into any details, but the cosmic microwave background, which I'm sure you heard about, the polarization of the microwave background on the sky and its statistical anisotropies give you a handle on the gravitational waves produced in the early universe at the end of inflation. And depending on the model for the inflation, this background has a particular slope in frequencies, and there are some models which can be already ruled out because their extension would be inconsistent with LIGO. And LISA in the future will do that even better. Here I call this multi-messenger because you're using cosmic microwave background radiation and some gravitational wave detector at much higher frequencies. Dark matter, this I think you'll probably hear about this also later. It's not just gas that can be surrounding the coalescing binary, for example. It can be that for certain types of dark matter particles, which can self-interact, for example, one of the black holes can be endowed and with its own cloud of dark matter, which then changes the in-spiral waveform. The companion can be actually suffering friction going through this dark matter cloud, and you change the waveform. That technically that can be measured just with gravitational waves, but again, if you know which galaxy this is happening in, you'll know a lot more about the physics driving this acquisition of dark matter spikes. Then there's neutron star equation of state. Neutron stars are unlike black holes; they're not point masses. They have material extensions, and the merger involves how compressible is the neutron star, and that also determines what kind of gamma ray burst you produce. So another big topic is to probe the neutron star's equation of state. And the naive statement is how compressible it is. And you can do that with both gravitational waves and electromagnetic observations, or possibly even neutrinos. Okay, that's it. It was a lot. Hopefully you remember some of this. The practical stuff is just maybe kind of more obvious. If you have a gravitational source that's marginal, you're not, some marginal likelihood that it's just noise. And then if you look on the sky and you see a flare at exactly the same location and you convince yourself it's the same object, then now you can have one more gravitational wave source to your catalog confidently. The other point is, if you generally, I assume this is also something you have heard already or will hear next week. The localization on the sky of gravitational wave sources is very poor. Unlike with a telescope where you see exactly where it's coming from, it's very poor. And this could be an issue because there are degeneracies. When you analyze the gravitational wave detection, there are degeneracies. For example, for a case of a binary, the inclination of the orbit and the distance of the source can be degenerate. Now, if you, and the sky position of the source can be degenerate with these other parameters. So if you have an electromagnetic detection and you pin down both the distance and the location of the sky, you can break degeneracies in your gravitational data analysis. That's also very useful. Okay, I'm done with this super long slide. Any questions? Yeah. Yes.
So combined astronomy
So probably not, because the temporal coincidence for a neutrino and the gravitational source can be so, the false alarm rate can be very low. Even though you don't know where the neutrino came from very well on the sky, if it came coinciding in time with the gravitational wave merger, you could associate the two reasonably confidently. right? So, okay, so that was my plan for the remaining of my lectures. So I think I at least want to definitely explain to you two things. One is that how do massive black hole binaries form in galactic nuclei, and what the role of gas is there. And the second is what kind of electromagnetic signatures we expect from a coalescing and then merging black hole binary in a galactic nucleus. Two other questions I could get to, we'll see. One is, if people are interested, I can actually make you vote. Where do these massive black holes come from in the first place? The other is the stellar mass binaries. Is it true that they're only vacuum, or can we have some models where stellar mass black holes formed in LIGO also produce electromagnetic signatures because they're surrounded by some gas? Let me start with the first topic here, pairing of massive black holes. Oh, I gave away, I don't know. I like to, since we're talking so much about black holes, I still like to pose this question. Well, I gave away something, but do you know who coined the word black hole? Raise your hand if you know who coined the word black hole. So, yes? Yes? So the reason I keep asking this question, because black hole, this is non-scientific. 1 minute aside. This is John Wheeler. Everybody, I think even the other lecturers, most likely will say John Wheeler came up with this expression. But then I read his autobiography recently, and which was published in '98. This is the title of his autobiography. And he says the following here. In 1967, he was invited to NASA's Goddard Institute for Space Studies in New York to give a lecture at a conference, which was on pulsars. And then this is what he says. The center of the pulsar is a gravitationally completely collapsed object. I remarked, one couldn't say this gravitationally completely collapsed objects over and over. One needed a phrase that's shorter. How about black hole? Ask someone in the audience. I find this very amusing. Apparently, according to his own recollection, John Wheeler took this from an anonymous person. For me, it was personally very interesting because my office in Columbia University, this was my view, and this place, Goddard Institute of Space Studies, this is Broadway. It's right there behind this building. This is that building. If this is much better in the United States, because do you recognize this? So this is the corner of Broadway and West 112. This is the famous logo of Seinfeld, the soap opera. But upstairs is where Black Hole was born, the name, due to an anonymous person. I tried to find out who this person was. Vittorio Canuto was still there when I was there. He remembers the conference. He doesn't remember the episode. So that person never came forward. It's anonymous. Also, this place has been in the news last 2 weeks because it was defunded recently. So it's actually closing. Okay, that's the non-scientific part. So let's return to science. So the first topic I want to discuss, how do black holes merge in galactic nuclei? And why do we think gas is there, and how does that help? So, and again, I'm going to go very slow. You should interrupt, make sure everybody understands. So there's a first, I'm just going to put together a story with very known facts, empirical facts. So the one fact that I already mentioned is that most galaxies contain supermassive black holes. That's good news if you're looking for gravitational sources. And the mass, which has been measured between million and 10 billion solar masses, correlates with the host galaxy's mass. Roughly 10⁻³ of the host galaxy is the black hole mass. And we know this, I think maybe I think you guys probably all know this, but I just want to emphasize that the best known case, of course, is at the center of our own galaxy. This is a picture showing about 10 stars in the center of our galaxy. This is done by, under, I guess, this group at UCLA. There's another group here in Europe, in Germany, by Reinhard Genzel, doing similar thing. What they did was this, they followed the motion of these stars over tens of years. And this 0.05 arc second that's shown here, I just want to make sure you appreciate, this is an angle, 0.05 arc second. That's roughly 2 meters. And if it's 2 meters in New York, and you look at the angle from Vienna, that's roughly this angle here. This is a ridiculously small part of the sky. And this is a movie. This is a movie which shows the motion of the stars, starting in '96 and then ending, well, that was 30 years ago. And you see that the motions trace these ellipses. And you can figure out that there's a black hole here, and the mass of the black hole is measured to roughly 10% accuracy, just by this orbital mechanics. Very simple, at least in concept. And we know for sure there's a black hole there. And of course, now we know even more for sure, because this black hole was imaged in the radio by the Event Horizon Telescope 3 years ago. And it looks like that. And it's actually resolved. Essentially, the few times the Schwarzschild radius is resolved in the radio. This black hole is definitely there. We know its mass. It's an unknown galaxy. Now, the problem is you can't really do this analysis of following individual stars and infer where the focal point is and what's the mass. But you can do the same exercise statistically. So if you look at nearby galaxies, this is a spiral galaxy. This is an elliptical galaxy. And you essentially can do the same exercise, but statistically, you look at the Doppler shift of the combined light of many stars or gas that's moving around the nucleus, around the black hole, and you get very high velocities, very close to the center, whatever you can resolve in your telescope. There's about 100 galaxies where this exercise can be done. You do the same thing. I mean, you basically infer the black hole mass from this equation. Of course, this is much more difficult in reality. You do orbital dynamics, and if you see the stars, you do some statistical fitting of the orbits of the stars. But the heart of it is this equation. If you see very large velocities, and if you know the size of the system is, then you can infer the black hole mass. They come out to be this million to billion. And the key point is that of the 100 galaxies where this can be done in the relatively nearby universe, because we can resolve the nucleus at least to do this, even if not the individual stars, they all have a black hole. Then we can extrapolate from the 100 galaxies to the 1 billion galaxies and say, well, if you have a billion galaxies, you took 100, every single one had a black hole, they probably all billion have a black hole. That's maybe a slight leap, but it's very likely most galaxies have a black hole. You say that, if you haven't heard this, that the Event Horizon Telescope could detect one black hole in M87, which is kind of amusing because this galaxy is roughly 1,000 times farther than the center of the Milky Way. But the black hole is 1,000 times bigger, so it's roughly exactly the same angle. This is like the sun and the moon on the sky. The exact reading factor of 2, it's the same angle. So therefore, the Event Horizon Telescope could also detect this black hole in the radio. So this one, we're also sure is there. And we can measure from this image its Schwarzschild radius. And it agrees with the measurements based on stellar dynamics. Okay. The masses, as I said, correlate. So this is one of the famous diagrams from a review paper. This is the black hole mass. This is the mass of the bulge. So the smallest side here for astronomy details, correlation is with the so-called spheroid of the galaxy. So big galaxies tend to be ellipticals. The entire galaxy is a spheroid. Smaller galaxies tend to be spiral galaxies with a central bulge. And then the central bulge is the spheroid. When you say bulge up here, it's elliptical galaxies. Then there's this pretty high correlation. To a further 15%, you can predict the black hole mass if you know the spheroid mass of the galaxy. That's what I mentioned earlier. Very puzzling. A big question: how does the galaxy know about the black hole, or vice versa? Which we'll come back to. Now, what about early galaxies? So here we think we understand the population of black holes, at least crudely, all the way from early universe to now, in the centers of galaxies, because we see quasars, and quasars are powered by massive black holes. There's no other really good theory what could be powering them. And this is the number of quasars per unit volume. This is magnitude, so the function of magnitude. These are very bright quasars. These are fainter quasars. They're more faint ones than bright ones. Redshift 4, 5, 6, 7. So we've mapped out this evolution all the way to redshift 7. This is the population of supermassive black holes powering these sources. And they exist, at least, in fact, the record holder is at redshift 10 from James Webb Space Telescope. This one. Okay, good. So point number one, galaxies have black holes in their centers. Now, the point number two is we know that galaxies build up in our favorite cosmological models and also in observations by mergers. A typical galaxy experiences several mergers per Hubble time in its evolution since the early universe. And we know this, as I said, from theory. All I want to point out here is that we have really well-developed theories of cosmological structure formation. This picture shows one of these big cosmological simulations from Volker Springel at Max Planck Institute in Garching. This is the cosmic web. Each knot in the web is a big galaxy. Along the filaments, there are other galaxies. This cosmic web evolves over time, and you can observe that these galaxies here, for example, will probably all merge over time into a single big galaxy. So these mergers are well understood theoretically. You also see them on the sky. You don't have to just believe the computer. We see interacting galaxies in various stages of mergers. This is a pretty well-established point that galaxies build up by mergers, from small to big. Okay. So now we have a situation where the galaxies, which carry black holes and they merge, the few times 10 million solar mass black holes tend to reside in, as I already explained, in spiral galaxy bulges. And so these are most relevant for LISA. The ones that are relevant for pulsar timing array, they're big black holes, 10 to the 8, 9 solar mass black holes. They reside mostly in elliptical galaxies. But these elliptical galaxies are not, so some people say they're dry because they don't seem to have a lot of gas left. But they just want to emphasize that even in these galaxies, in the ellipticals, if we go back here, maybe this is getting very astronomical, but it's important to point out that spirals, we have a lot of gas, they're forming stars, they're gas rich. Elliptical galaxies, they're very red. Stars are old, and there's not much gas left. But if you look in the nucleus with radio telescopes, you do see emission from gas. So there is gas there. And all you have to have is a mass of gas comparable to the black hole mass, which is 0.1% of the stellar mass. And it will be important in principle for black hole dynamics and electromagnetic emission. Okay? So the last point is, okay, actually one. The last point is, okay, what happens when two galaxies merge and each one has a black hole in the middle? Well, this is another thing that's pretty well established over the last few decades. And essentially, both the gas and the black holes go to the center of the remnant galaxy, the merger remnant galaxy. I just want to emphasize, well, I want to explain both of these points very quickly. In terms of the gas, there's this paper from 30 years ago by Lawrence Hernquist and Josh Barnes. which did the first hydrodynamical simulations of galaxy mergers. And they identified the physics that's important here for driving the gas down to the center of the merger remnant. So tidal forces during encounters cause otherwise stable disks to build bars, and gas in such bar disks subjected to some sort go towards the central regions where they fuel starbursts. So they weren't particularly interested in black holes in this paper. They try to explain empirical observation that merging galaxies produce bursts of star formation. But for us, the key point is that the gas collects in the center of the merger remnant. So this is the distribution of stars again, this is historically interesting. I mean, this is one of the first simulations where the stars are represented by n-body particles. These are two galaxies which are set on a course of merger in these nearly parabolic orbits. They go through a sequence. This is time on the top right, so it goes through this sequence. And the scale here is about 100 kiloparsec. You see the stars get tidally deformed. Now, the interesting point is that this is the same simulation has gas. This is one of the first cosmological hydrodynamical simulation where SPH, smooth particle hydrodynamics, was implemented. So you could also follow the gas. You see it's pretty messy, but what you see here is this dense ring of gas in the center. And this scale of this image is actually 10 times smaller, not 100. You're looking at the inner 10% of the previous image. And this is just a direct comparison of gas and stars at each stage in the central region. You look at this one, for example. The gas is here. This is the stars. The gas has shrunk to a much smaller distance. And the physics of this has been explained. Is the direct gravitational torque during the merger that starts to drive the gas down. And afterwards, an even more interesting piece of physics, which is if you look at these bars, which form due to gravitational instability, you look very carefully, they're not aligned. They're slightly misaligned, the gas and the stars. And the stellar bar forks the gas bar and removes angular momentum, and the gas flows in. This is what causes dense gas concentration in the nucleus. Okay? So that's very good again for multi-messenger astronomy. This is resolved down to maybe kiloparsecs on the simulations. Now, the second point is the massive, question. Maybe that's a very broad topic. There is a whole topic of angular momentum of the gas in a galaxy formation. I think what I said here is very uncontroversial. In a merger, the gas occupies a region that's at least an order of magnitude smaller than the stars and goes towards the center. Now, exactly how big it is debatable. Maybe I'll talk to you about this separately. In fact, if you don't do anything to the simulations, you cannot reproduce galactic disks. Everything, or the gas becomes too small. There's a tension with observations that you have to keep it some angular momentum to explain the disks. So the second point is maybe more familiar to people, which is that you have a very massive black hole in this merger, two of them, and they shrink to the center. This is just cartoon. The process initially there is just dynamical friction. Can you raise your hand if you've heard of dynamical friction? Okay. If you have not heard of dynamical friction. Again, just for these 5-6 people, this is the cartoon. If you have a very massive body, this was studied by Chandrasekhar, the famous Chandrasekhar limit. Chandrasekhar, who also did this important work in 1943. He considered uniform gas cloud, or actually it doesn't have to be gas, uniform collection of particles whose masses are very small, and a heavy body is moving through in a straight line without acceleration. what happens is the gravity of the massive perturber diverts the trajectories. So in its frame, all the particles are moving backwards, and they're diverted by gravity, and they form an overdense wake behind, which pulls the particle back, which pulls the massive perturber backwards. This removes velocity. It effectively decelerates the moving body, the moving big body in the sea of small bodies. You can work out in approximations. This is effective force due to dynamical friction. And for a big black hole moving through the dark matter and the very low mass star, much more lower mass stars, this means that it will spiral inwards and end up in the nucleus. A big black hole. Okay? I think this part has been, this is the uncontroversial part. If you have a galaxy merger with two massive black holes, you'll end up with a pair of black holes in the middle, surrounded by dense gas, on at least the scales of kiloparsec where other things can become important. Now, do we know this observationally? Yeah, question? Yes. Yeah. So the gas ends up in kiloparsec scales, and it's still then in the disk. You form an accretion disk. So after it's on kiloparsec scales, I should maybe explain this more in detail, but it forms a disk. The reason it forms a disk is that it has some angular momentum left, but it radiates, so it loses support in one direction and has support in centrifugal support in a plane. Now it's a disk, and these disks have viscosity. So they slowly, once you have a disk, you can't avoid some kind of accretion towards the center. You will actually drive gas continuously towards the center on timescales which depend on the source of viscosity, which is not fully understood, but maybe I'll comment on it in a second. Initially, it's just gravity. Gravity makes the disk very lumpy and causes angular momentum to be transferred outward. Gas is flowing inward on timescales which are quite fast, tens of millions of light years. I think it's also uncontroversial that you're just feeding gas to the much smaller central regions. Okay. Observationally, can we confirm this? I claim uncontroversial scenario. The answer is not really easy. But this is the poster child of an active pair of black holes. This is an X-ray observation. There are actually two quasars in the nucleus of this galaxy, NGC 6240, separated by about a kiloparsec during a merger. And the problem is it's very hard to resolve lots of cases, the much smaller separations. There are many examples of wider binaries in optical observations, 10 kiloparsec or larger. They're called dual or offset AGN. The record holder is actually in the radio. There is a source in the radio where you have interferometers, and you can, this source, Rodriguez et al. 20 years ago, with a very long baseline interferometry, they resolved two point sources separated in projection by 7.3 parsec. That gets pretty small, but you should ask, okay, but we want a bound binary black hole. So the criterion for that is that the black hole should be separated by less than a sphere of influence, or even more obvious statement is that the mass enclosed by the orbit of black holes should be dominated by the black holes, not by something else. If it's something else, you don't have a binary. You just have two black holes moving around in some stuff. If the black holes dominate the gravity, then you have an actual bound binary. Now, because we know the velocity dispersion, at least along the line of sight in the spectra of the nucleus of galaxies. This separation for a 10 to the 8 solar mass black hole, when the velocities, which correspond to Keplerian velocities, are 200 kilometers per second, that's typical value, it should be 10 parsec. In fact, this one source is kind of marginal. It could be a bound binary on the borderline. And it's the only one. We don't have any solid example in observation of a spatially resolved gravitationally bound binary. The obvious explanation for this could be that they shrunk quite rapidly to smaller separations where we just can't resolve it. Now, can you actually merge and make a gravitational wave source if you have such a binary? So here I like to emphasize the number. So if you have in vacuum, two black holes separated by some distance, they will spiral in due to the emission of gravitational waves. I'm sure you learned the details of this, how fast this happens in other talks at this school. But as you all know already, the in-spiral accelerates. This is a very steep function of separation. In fact, the power is the fourth power of the separation. So in the beginning, this in-spiral is very slow. If you make the black holes more compact, it accelerates and becomes quite rapid. So there is a radius or a separation where the in-spiral would take a Hubble time. And everybody should know this separation and appreciate that it's small. So if you want the in-spiral to happen in Hubble time, for a 10 to the 6 solar mass black hole, you have to start from 10 to the minus 3 parsec. For a very large 10 to the, this is the largest ones we know about, they should be at a parsec. If you want to merge these black holes in a Hubble time, it's actually not enough. This process that I described is not enough. There's a large number of orders of magnitude in separation that you have to overcome before you have a chance of a gravitational wave source. How does that happen? This is sometimes called the final parsec problem, because when this was first noticed, people were focused on this very massive, and it's anyway just an order of magnitude estimate. For the 10 to the 9, 10 solar mass black hole binaries, you have to get to a parsec somehow. Sometimes this is referred to as the final parsec problem. It's a problem if you want to build a gravitational wave detector and make sure you detect something. It's a problem if you don't cross this barrier. So this is another famous paper from 1980 by Mitch Begelman, Bamford, and Rees. These are schematics, and this shows R over R dot. This is the time spent by a binary at various separations. So the parsec that I talk about is here, 1 parsec. This is 100 parsec. This is 10 minus 2 parsec. And you want to be somewhere here. So this line here, there is the gravity TGR. This is the in-spiral time due to gravitational waves. And this is for a 10 to the 7 or 8, 10 to the 8 solar mass black hole. This is actually closer to the lower mass end that I mentioned. So this has to be about 10 minus 2 parsec to merge in a Hubble time. Hubble time is here. Okay. This is the dynamical friction time scale here. It's very fast. It's 1 million years. Can you see here? So at large separations, the black holes are just approaching each other due to dynamical friction. This is easy. Once you know the background density, typical background density of stars in the nucleus. And then this dynamical friction is happening on the stars. And what happens is then this timescale becomes very long because, unfortunately, if you have stars and you're interacting with stars and you're a binary propeller and you do dynamical friction, the idealized case I showed was a perturber going on a linear motion through an infinite homogeneous medium. You can have eventually slow to 0 speed and come to rest with the medium. This is a bit different. This is circular orbit and in spiral. and you keep ejecting the stars that you're interacting with. So what happens in here, when you're about a parsec, you've ejected all the stars. That cause the dynamic of friction shrinking. And this time scale shoots up to be much longer, well, longer than a Hubble time. This is called the final parsec problem, that you have to somehow rely on something else to make sure the merger happens. Now, you can still interact with stars in the nucleus because you're a propeller. The binary is going around, interacting with stars and shrinking, and then it's stalling because you ejected all the stars. But very far away, their stars sometimes scatter among themselves, and they're scattered onto orbits, which take new stars and replenish the lost stars from the nuclear region. This is called filling the loss cone. And so if this loss cone was completely full all the time, meaning you scatter stars at a rapid rate and you keep supplying new stars, you could actually merge in a Hubble time. You could reach this small separation, gravitational wave take over and emerge. The problem is you tend to deplete this region. This is another topic. It's not my expertise. There's many papers on this subject of how efficiently you scatter stars to interact with your binary when it's in sub-parsec stage. I think I'm going to skip some details because I'm very slow by now. I'm going to just say this in words. That this, if you take a simplest model, a spherical cluster of stars, and an equal mass binary black hole, this process of refilling the inner region is very slow. So it would not work. The binary would stall for longer than the age of the universe. If you have various asymmetries, so that stars scatter more frequently, for example, your stellar bulge is triaxial, and your black holes are not equal mass, but 1 to 10 mass ratio, then it's possible to send enough stars to the nuclear region to cause the merger within a Hubble time, but it's still pretty long, billions of years. You will be hung up in this stage. Does that make sense? Now, the good thing is that, in fact, this paper only mentions, like in 2 lines. It says here T gas 10 to the 8 years. It's actually not really a calculation, it's just a cartoon. But in principle, as I said, there's also gas in the nucleus of the galaxy. We have a description of how this gas behaves. This is a cartoon, another cartoon of a quasar with its accretion disk. So here on this cartoon, this is about a parsec. This is a black hole here, supermassive, 10 to the, let's say, 8 solar masses for concreteness sake, driving a jet, which is not important at the moment. The important points are this disk here. We have models for this. If this was a school on accretion physics, we could spend lectures on how these accretion disks operate. For us here, the crucial point is we have these models which predict how much mass is in the disk. Obviously, as you go to larger scales, the mass in the disk increases. So out here, around the parsec, coincidentally, you reach a point where this disk is self-gravitating and becomes unstable to perturbations. So this is a well-known problem also for decades, that these outer parts of the disk are unstable. Inside the parsec, the disk is completely stable. If you make perturbations in the linear perturbations theory, it is stable. So it will happily accrete inward. So now comes the question, what happens if there are actually 2 black holes? Initially, the 2 black holes are separated by more than a parsec, so they would be embedded in this unstable part of a big disk. And I just show one result on this from a group in Zurich from 12 years ago. These are hydrodynamical simulations, which show, you see 50 parsec is here. This is in the nucleus of a galaxy. And the disk has become unstable and form all these clumps. And if there's 2 black holes here, which you don't see in this picture, if there's 2 black holes, this plot on the right shows in various suite of such simulations the separation of the two black holes as a function of time over millions of years. The takeaway message from this is that it's a zigzagging process. You put a black hole here, it will interact with these clumps, but overall, this is not obvious. It was found in the simulations. So unlike the other things I described, which is kind of obvious, the black holes keep shrinking. Here that was not obvious, but it is the result from the simulations. The separations decrease, and they actually do pretty fast. 10 million years, 20 million years. They go down to, well, in this plot, you can't really, in these simulations, you resolve maybe 0.1 parsec. So that's very good. That result has been very confirmed with several other groups in the last 12 years. Now come to finally something I'm doing myself. I'm most happy to discuss, which is what happens afterwards. So now you have two black holes which successfully maneuver down here, well faster than the Hubble time. Now you have two black holes sitting in this stable part of the disk. I like this problem because it's much less messy. You have a very nice coherent Keplerian disk with 2-point masses. And you want to ask the question, what happens to the black holes? So I think I'm going to skip a lot of the next few slides because I have about 5 minutes. So I should say that this question, what happens to 2-point masses embedded in a thin disk, can be approached. I like to divide into 0D, just pure analytic calculations, 1D models, 2D simulations, and 3D simulations. All of this has been happening for the last 15 years or so. I think the analytic models are very nice, but really there are very strong non-axisymmetric perturbations here. So really, I think I just skip 0D and one-dimensional calculations. It's very hard to get anything that is close to correct. Ultimately, you have to do at least a 2D simulation. 2D simulations or 3D is even better. The problem with 3D simulations is that they're expensive. In fact, you should really do 3D. Okay, so if you had infinite computing power, what you should do is 3-dimensional simulations in numerical relativity with hydrodynamics and include radiation transport and magnetic fields. So you should do 3D, GR, R, MHD. This is very expensive, but such simulations, in fact, recently have become possible, but you can only do, let's say, 3 orbits. This is maybe in the next 10, 20 years, things will improve, and we will be like numerical, I don't know, is there numerical relativity talks at the school? Somewhat analogous. I'm old enough to remember that the first numerical relativity simulation solving Einstein's equations for a binary happened around 20 years ago. People could do only 1 orbit or half of an orbit. They were very happy when their codes didn't crash and they could do it. Now you can actually do tens of orbits or even 100 orbits in numerical relativity. Here you have to add magnetic fields, radiation. Very difficult. The problem, so this is just to justify why I myself work on 2-dimensional hydro simulations. The advantage is you can't get all the physics at the end, especially, but you can follow long-term evolution. That's very important because if you set up a 3D simulation, you have to decide the initial condition. So we at least want to first understand what's happening as the binary is shrinking from a larger scale. And in that case, relativistic effects are not super important. And the disk is very thin, so 3D effects are hopefully not super important. So I was going to explain next what happens in these 2D simulations. Okay, but I should say one more thing. So this is all to justify doing 2D hydro simulations. And there are really 3 things you can get out of these doing 2D hydro simulations. One is, by the way, when I say 2D hydro simulations, what I mean is we solve the Navier-Stokes equation, so 3D hydro, but we integrate out the z direction, assuming the disk is very thin. Question? Yes, I'm going to talk about this, but yes. So yes, but there's actually very interesting questions about eccentricity. So what you say is the dynamic of friction pairs the black holes. It's almost for sure eccentric. But you're still at parsec. You're way, way before merger. I think that's almost irrelevant to gravitational wave detections. So, but even before gravitational waves circularize, you have to ask what happens to the surrounding gas because you're not even in the gravitational wave driven stage. I'm just saying, if you go to this cartoon, so this is a parsec here. So maybe out here, below parsec. So this binary might be quite eccentric. You have to ask how does the eccentricity evolve here, and when the binary is here, already very small, parsec. It's way, way too weak to emit gravitational waves. It's about a factor of 100, too wide to measure, to emit detectable gravitational waves. That's what I'm going to describe, what happens to eccentricity at that stage. So hold your question because I'm going to talk about it. But I think we're at 10:20, so I think maybe it's a good time to stop and just flash this. 2D hydro simulations are great. I will describe to you tomorrow how the orbit evolves, including eccentricity, and what kind of signatures come out in photons. But so there's basically three things for tomorrow. Electromagnetic signatures. How does a in-spiraling disk-embedded binary differ from a single black hole in terms of its light curve and spectrum? How does the orbit evolve over time of the black hole binary, including eccentricity? And then the third one is, does the gas still impact the gravitational waves and make it deviate from vacuum? That's for tomorrow then. And I don't know how this works, so I'm happy to answer questions if you have any. Thank you.